Hi, this is Jeff Heaton. So I just gave a couple of conference presentations and I want to give some of the material here in YouTube. So this is a somewhat condensed, quicker version of what I spoke at the conferences about. We're going to start with feature engineering. For the latest on my AI course and projects, click subscribe and the bell next to it to be notified of every new video. This is a presentation I gave yesterday at the 2019 Predictive Analytics Symposium by the Society of Actuaries. This is on multivariate feature engineering. So first of all, why is feature engineering even needed? The dream of artificial intelligence, in particular neural networks, is to have end-to-end feature engineering, where essentially the model learns all of the transformations that need to happen on the data before it goes into the model. So there's a lot of companies out there right now that are working on AutoML. You see a couple of them floating about here. These companies are all using machine learning and some other automated tasks to try to basically do feature engineering, model selection, all these kind of things that data scientists do on their own in an automated way. You might think, okay, they're out for the data scientist job. And that's fine. Data scientists are out for everybody's job, even their own. Well, not necessarily. You get the idea. But who is out for the AutoML guys' jobs is deep learning, where you truly try to get end-to-end machine learning in a single model without having to do all of the stuff that the AutoML guys are going through to try to optimize and find feature encodings and things by using a hodgepodge of techniques to bring them all together. End-to-end machine learning is just not completely there yet. For things like chess, it's great. I mean, you needed no domain knowledge of chess whatsoever for AlphaGo 0, where they were able to, or Alpha 0, where they were able to master Go and chess and a few other games completely without previous human knowledge, just by doing completely end-to-end, letting the machine learn it on its own. Feature engineering may be there at one day, but for now, it's good to have some domain knowledge and learn how to represent these. So let's see, why do we really need this? I'm going to show you a few examples. First, I'm going to show you why models are bad at extrapolating. This is important to understand. When a neural network is learning a feature, or other models as well, they're fitting a curve to something. They're not actually learning the actual equation that you maybe put together, or the procedure algorithm that you did to learn that. So let's see really how bad models actually are at extrapolation. So what this code actually does is I am creating the sigmoid. So it creates the kind of S-shaped curve that the sigmoid function has. We're going to try to predict that by training the neural network on some samples within the sigmoid curve and then try to predict outside of where we've trained. These are the Y values that I have. Now I'm going to create a neural network and train it and fit it to that sigmoid curve. It's important to understand it's learning the curve. It is not learning this equation at all. So our score is very good. Our MSE is 0.01. We could even get that lower, more likely. And you have to remember too, I picked random values out of the sigmoid sample. So it doesn't have the full perfect sort of sigmoid curve that you would have if you picked everything. We'll look at the data set and you can see the random sample points that I picked. And that is what the neural network is trained on. So it's given a huge number of samples, but 40 or 50 since we're starting at 0. And then I run this and you can see where it tries to predict. I try to predict across this whole area, -40 to +40. And it simply was not trained much outside of that region that you see there. So you can see it's fitting the curve pretty well inside of the training set, but it just goes out like crazy because the neural networks are very similar to polynomial functions. And you know, those extend to positive and negative infinity off of both ends of the graph when you extrapolate it. So this is good for feature engineering. If you truly create the equation that represents something underlying that you suspect is important, like a BMI or some other ratio or difference that you want to set up, you're a lot more resilient to dealing with data that is coming in out of your range. If the neural network gets data out of its range, it tends to go a bit crazy, like you see there. But if you have engineered that feature, it's probably already moving or normalizing the data into a specific range, like a BMI or something like that, before it even gets into the neural network, and you have much less of a problem with this. And you might think, okay, well that's obvious. Don't send data to the neural network that's outside of the range. Well, this is univariate. Multivariate, it's much more difficult. Say you're dealing with medical data and you know, okay, I only have blood pressures within this range. Well, then what if you also start to predict on male and female? How many males do you have within that range? How many females? Then you start to put age in. For certain age ranges, how many blood pressures do I have in a certain range? If you're dealing with a very young segment of your population as well, maybe the, 15 to 20, you're not going to see a lot of hypertension in there. So your neural network will somewhat freak out when it sees that, because that is a multivariate extrapolation now. If you did not have any training data that really covered that, where the hyperbolic and systolic go outside of a certain range in a certain age range. So be very careful of multivariate extrapolations as well. Now this is related to a paper that I published for the IEEE, and you can just Google Scholar the name of the paper there. It's been doing well. It's been getting a number of citations. I essentially wanted to look at a whole variety of equations and in an empirical way analyze which of those the neural network and 3 other model types, random forest, gradient boosting, and support vector machine, were able to synthesize these formulas. The reason I did this is if you are going to have your model already synthesizing some features for you, you don't want to redo the work that your model is doing. If your model is able to figure out, say, differences, and it does pretty well, you probably don't want to spend your time figuring out how to engineer that particular type of feature. So I ran it through all of these. This was also a publication I did with the Society of Actuaries called a math test for models, and it is truly that. It's essentially a math test. So say for the difference column, you could almost think of this as going to Microsoft Excel and, just entering random numbers. There is much better ways to enter random numbers in Excel than this highly probably biased way that I'm doing it. And then you essentially just put in a formula, and that minus that. And what I literally did is generated data where C is now going to be the Y, and X1 and X2, the predictors, were A and B. And I saw which of these equations the neural networks were able to solve better. And it's not like they're solving the equation. The neural network is not internally realizing that, okay, you're subtracting 1 from 2. It's fitting a curve. And that curve is not going to extrapolate the equation well at all once you get outside of the range. Now, I wasn't even trying outside of the range on this. I was just seeing, in general, 50,000 or so input points. How well can the neural network really fit the curve for each of these types of equation? And you can see the results here. I'm just showing you for neural networks here. The higher the bar, the worse it did. Like a BMI, counts, standard deviation, it did kind of okay on. Difference, log, polynomial, power, and so on. There it does not do, it does much, much better because it's a much lower RMSE. The RDiff, the ratio of differences, this one here, it just does really bad on. And I'll give you a hint on that too. It's got a division by 0 in there. That never ever helps. And this is also very small values because these are all uniformly sampled from the same range. So I could have perhaps even normalized these results by the range on each of these, because some of these equations have much bigger ranges, y values coming out, than others. But there's no noise. We're truly trying to see how well can the model fit to that equation. So I would expect all these to be able to get to 0 RMSE. Well, actually, I didn't expect it, but if it truly was synthesizing the formula, it should be able to get to a 0 RMSE. But they're not. They're just curve fitting. I give you the code here for the ratio of differences, so you can run that. The paper has the entire code published online, so if you want to rerun the entire experiment, the code is definitely there to let you do that. It's not that long, but it does give you the code for that. This is running it all through a gradient boosting regressor, and you can see the RMSE is around 22, which is not good at all for the ratio of differences because it gets really small values. Target encoding. I also have an entire video on target encoding, but this is a technique that's very popular in Kaggle. Let me just run it. I'm generating some sample data here. This is a way of getting categorical values down to lower dimensions. Categoricals, usually you do dummy variables. So if I was categorical encoding this cat 0, I would have dog and cat. That would be 2 dummy variables. That's not bad. You could even not have 2 dummy variables. You could just put a binary in there, a 0 or 1. But what if you have the 50 US states? What if you have all the counties in the country? Well, you should probably think of a better way to encode it than dummy variables because you're going to have a ton of them. This is a way that you can deal quite easily with a ton of dummies. You could have maybe 5,000 of them in this category 0, and the target encoding of it is going to be just one column, a number that is replaced for the categorical. I can explain the simple case of target encoding really pretty easily. You would essentially put in a constant value for dog and another one for cat, and essentially replace those. So dog, what you would do is you would look at the target, hence target encoding, and you would sum up all these values and then divide it by the count. So it's the count of dogs. So it is truly just an average. You are looking, what is the average target value for dog? What is the average target value for cat? And you put that value in for cat and you put that value in for dog. Now this is a dangerous technique. It works well, but it's dangerous. It's really prone to overfitting. And when I first saw it, I don't know, I was very dismissive of it, but I've seen it do good things in Kaggle. The problem that you have is, first of all, anytime that you see the Y or the target used before evaluation or before training as part of feature engineering danger, you are target leaking. So here we are truly doing some target leaking, and it's going to cause it to overfit. Where this is really dangerous is in category 1. Say we wanted to categorically 1 encode this, and it would be okay for wolf because we would essentially take the average of all those wolves, but there's only one tiger. So we would always replace tiger with 0, and that's massively overfit. So the way that you solve this is you put in essentially a hyperparameter, a weighting, and that weighting determines how much you want to weight it towards the overall mean. So the overall mean or the overall average is for Y completely, and then you're weighting that together with the mean for tiger. So if you said 50-50, it would basically calculate the overall average and then the tiger average, which in this case would be 0, and it would take half of the tiger average and half of the overall average and sum them together, and that is the value that would be put in for wolf and tiger. You'd have a different value for wolf and a different value for tiger because the half of it that was coming from the overall average would be the same, but the half that's coming from the category average would be different. And I give you some code here that you can try around with that and see what the averages look like. Here's how you actually put it in to replace the categories. You can also use neural networks for feature encoding. This is autoencoders. You can use a neural network to reduce the dimensions, just like a PCA or TSNE. The way an autoencoder works is you have essentially the same number of input neurons as output neurons. So in this case, we have 5 inputs, 5 outputs. So we probably had 5 predictors. We're trying to reduce the dimensions in this case to just 2. So essentially what's happening, you train this and the X and Y are the same. The X and Y are both the predictors. So it's unsupervised learning. There is no Y. And just like TSNE and PCA are both unsupervised learning because there also is no Y. So what this essentially does is almost creates a custom compression algorithm for you, a codec. This part's the encoder, this part's the decoder. And the neural network learns to become that encoder and decoder. This also becomes great for anomaly detection because data that you trained it on should probably make it through the encoding decoding process with minimal loss of signal. But if you take that trained neural network and you try to encode decode new data that's very different than what you trained on, your error rate should go up. You're trying to evaluate it now on data that it's never seen before that is quite different than the original data, and it won't compress. It'd be like trying to use JPEG to compress an audio signal. Just not what it was designed for. It's dealing with the Titanic data set. And the Titanic data set is somewhat actuarial because people are dying and you're predicting mortality. Do people survive? Survival analysis. Here you are dealing with all of this data, survive, passenger class, gender, so on and so forth. And what I'm going to do is essentially pass this in to the autoencoder without survived. We don't want to reduce the dimensions on survived as well. So I run it through this basic neural network that I set up. Now it's a little bit bigger than this neural network. I added a couple of layers in between here and here just to help the autoencoder and decoder. And you can see the results of the training there. Now, if I give you a summary of the model, it has its input and then 50, 25, 2. This is the autoencoder later, that 2, 25, 50, and then 9. And you might be wondering, where does that 9 come from? There were 9 inputs. So the input layer up here that you don't really see is also 9. We can hack off these last 2 layers like this, and you'll see basically now I have just the encoder, 5025-2, and I can use that to encode. And now we have the dimension reduction happening. There's just 2 dimensions here and here, and that is all of the Titanic data with the dimensions reduced. We can now do a nice plot of this. It's not working quite as well as you might hope as far as a visualization, because you see the survived and did not survive, but you can see some clustering going on where there's a lot of reds here. And you can actually train now a non-neural network model like a support vector machine or some sort of a classification model, and there's actually quite a bit of data packed into these 2 dimensions. It does pretty good at finding these regions where it survived or did not survive in the reduced dimension space. Another feature engineering technique that you can use are embedding layers. You hear a lot about this in deep learning. If you've worked with Word2Vec, this is essentially what Word2Vec is doing, but this is showing you literally how you can create your own embeddings. You can think of this almost like dummy variables. It is taking a categorical value and turning it into a vector, 3, maybe 4, however many you want values, but you don't need a embedding dimension for every single discrete categorical value that you have. This is why this is done in natural language processing. Frequently, you may have 50,000 words in your total corpus. You don't want 50,000 dummy variables. That would be well dumb. So don't do that. This is showing you how something like Word2Vec could be built up. I will go ahead and run this. This is essentially building a very, very simple neural network that just has only an embedding layer. The input dimensions are 10. Output dimensions, so this is how many it's reducing it to, is 4. So you have essentially 10 values. You want to reduce it to 4. And this input length of 2, that just says how many of this categorical value, how many times does this categorical value appear? You might think of this like sentences, where you may have maximum sequence lengths of 10 if you have up to 10 different words in a single sentence. So you would put 10 here, because often you will repeat these categoricals. If there's just 1, then you put 1. So this is essentially showing you kind of how this is working. So I said that there were 2 categorical values in here, and this is the same as this length up here. And the neural network essentially created a random encoding for each of those 2. So 1 gets blown out to this, because I said I wanted 4 dimensions that it's reduced to. And then 2 gets blown out to this, because I wanted that many that it was reduced to. Now this is not really a reduction, because we only had 2, but this is just showing you the simple case. Now if I were to put in this next row, so I had a 1, 2, now I put in a 2, 1, and I run this, now you get 2 values back, and you'll notice it does repeat. So these are consistent. The 1 was encoded to this, and also encoded to this here, because it's in opposite order for the next one. Now, if we look at the weights of the neural network, we can see this is actually pretty simple what it's doing. I said that we could have a total vocabulary size much bigger. You can see here is where these 2 rows are what we're dealing with here. These are the values that are being inserted in. You'll see that that matches up here, as does that one. This is just a lookup table. This is all the neural network is doing once it's been trained, and now you're scoring, is it's essentially doing a lookup table. It's really just like dummy variables. I could put in a 1, 0, 0, 0, 0, 1, 0, 0, so on, and it would just literally fill those in for me. Now what we want to do is to be able to actually see how that works. So let me go ahead and run one of these. I'll show you how it could be used literally to emulate dummy variables. Here I'm showing you a classic dummy variable encoding. Input dimension is 3, because there's 3 categories. Output dimension is also going to be 3. Now normally that'd be a warning. You're not really achieving anything here, because you're making the encoding just as big as the input, so you're not reducing the size, but that's okay. And we're still going to have 2 of those. So I run this, and now I query it. Here you can see for 0 and 1, it's basically doing dummy variables. That's showing you this is truly just a lookup table when you're scoring. That was a transfer. That's sort of like transfer learning. I transferred in the dummy variables. Now training and embedding, this is where you learn to create your own. And this is often used in natural language processing, but it doesn't have to be. It can be used any time that you have a large number of categories that you want to reduce. So this is a pretty simple example. These are reviews, so it's doing almost like sentiment analysis. These are the reviews. First ones are all positive, or negative. Second are all negative, and I did put a little bit of noise in here. So that one's actually misclassified, but that's okay. We're going to say that the total vocab size is 50. There's actually not 50 words. I'm just estimating. This does not have to be exact. It just has to be too big. And I'm going to encode the reviews so that basically it does a lookup. Never becomes word 14. You can see probably the two awesomes. See, yeah, 12, 12. They encode to the same value. And this is essentially just now a lookup. You would like for the lengths to be consistent though. So here I'm padding with zeros. So these are the same things. You can see some of the awesome ones there. And now I am going to fit the model to it. And that will fit the embedding layer. So it is now trying to find out the actual best embeddings that you can put into that lookup table that will best encode these words. If I print this out, you can see that's the embedding layer that it trained. So for each of those words, those 50 or less than 50 words that I have, each one was trained to have an embedding. So this is a dimension reduction in the sense that you may have 50 words, but there's not 50 elements there. And how big should you encode these down to? That's up to you. I mean, some of the versions of Word2Vec have 300, but that's also encoding a ton of words. And you can also see the accuracy just using the embedding, and it's 1.0. Now realize there's a little bit of noise in there because we've got the one classification, but the one misclassification, but this shows you how you can create your own sort of Word2Vec for your own words. Feature ranking becomes a very important part when you're doing feature engineering. So here I'll show you how to use something to do multivariate feature ranking, because you can rank several features together. Let me go ahead and run this. This is giving you the perturbation rank. I use perturbation rank a lot, so you've probably seen this from me before if you've watched many of my videos. I am going to now encode the Titanic data set. So there's the Titanic data set with dummy variables. Now I am going to fit a model to it. And be aware too, the Titanic data set, best ones on Kaggle I think get around 80%. You can't really fit this that perfectly. It's a tutorial and there's just a lot of noise. There's one child of a first-class passenger that died, which by all statistical analysis should not have. Some horrible mistake was probably made between her nanny and parents or something that resulted in her demise. But this is... You can't predict that kind of stuff. So now I'll show you the perturbation rank. And the way perturbation rank works is we take each of these values. So sex is the most important. Women and children first. So yeah, that's important. You might think age would also be as important, but that gets confused a little bit because it becomes very important for males, but not so important for females. It's still important for females in some cases. So this is working by basically taking a trained model, you don't refit it, and you one by one go through all of these. So you could multitask this. And for gender, you're going to basically look at the error with all of these in and with sex removed. Now, how do you remove a feature from an already trained model? That's not so easy. What you do is you take the data set and you scramble the sex column. Basically, like shuffling a deck of cards, you randomize it. You don't change any of the values, you just shuffle. The reason you don't change any of the values is now you are not introducing other biases in. You are not changing the max and the min and the mean and the mode and all the other values. All those statistics are remaining the same, but you've effectively destroyed that column. So you look at, this is what the error is when we do that to sex. It really hurts the predictive power of the neural network that we have in there. The importance of sex is 1, so it's the most important feature. Then we go through and we scramble each of these and compare. This is multivariate because you could scramble multiple together and do that evaluation. You could scramble the 3 dummies together and put the dummies back together and get a single feature importance for all the dummies. That's really handy because normally the dummies on most feature ranking algorithms come back separate. You could also look at sex and age together. How important are those two relative to the others? They're very important. So this is just a good function that I'm giving you here that gives you just a starting point for working with perturbation rank. I use this to evaluate my features and just give me general direction. You can also run it on many different pairs and see which things are highly correlated and are very predictive together, but maybe not so much on their own. And that gives you a way to know that, okay, you should maybe find some feature encoding between pairs of variables that are very important. Thank you for watching this video. This is just some information from a conference presentation that I had. If you like this sort of thing, please click the like button and subscribe to my channel. Thank you very much.